Have you ever stopped to wonder what the invisible link is between a simple electrical wire and, say, the force that moves a compass needle? I mean, they seem like totally different worlds, right? But they are connected by this secret relationship, one that's described by a single beautiful law of physics. So today, we are going to unpack Ampere's law.
Okay, so to crack this mystery, scientists did what they do best. They started observing. They started looking for patterns, for those first clues that would eventually lead them to a universal law.
And what they found was, well, it was beautifully logical. The more current you push through the wire, the stronger the magnetic field gets. Makes sense. And the further away you move from that wire, the weaker the field becomes. It's this really direct, kind of intuitive relationship.
And all of this whole relationship, got captured in what we now call Ampere's law. This is really powerful, super elegant answer to that first question we had, providing the exact mathematical link between the cause, the current, and the effect, the magnetic field. But, to actually use this law, we're going to need a pretty clever tool. And it's not something real you can hold. It's more like an imaginary gadget that makes all the math possible. This is where things get really cool.
Which, of course, brings us to the next big challenge. We know the field is all around the wire, right? But how on earth could you add up its strength at every single point in a perfect circle?
And that's where our imaginary tool comes in. What we do is we just imagine a closed loop circling the wire. We call it an Amperian path. Remember, it's not a real thing. Just think of it as the racetrack we're going to use for our measurements.
All right, so we've got our imaginary path. Now what? How do we use it? Well, we're basically going to take a little trip around it, step by step, to add up the field's total strength. Okay, so the process is kind of like taking a really detailed survey of this entire path. First, step one, we mentally chop up our loop into countless tiny little segments. Then, for each tiny segment, step two, we figure out the strength of the magnetic field right at that one spot. Now here's the crucial part, step three. We only care about the part of the field that's pointing in the same direction we're walking along the path. And finally, step four, we just add up all those little forward pushes from every single segment all the way around the loop to get one final total number.
To make that a little more concrete, just imagine you're walking along that circle yourself. And at every single step you take, you measure how much that magnetic field is kind of pushing you forward. Ampere's law is really just the grand total of all those tiny pushes, added up over your entire walk.
So, after all of that work, right? Imagining a path, breaking it into a million little pieces, adding everything up, you'd probably expect a super complicated answer. But the result that Ampere discovered, it's stunningly simple.
And here's the big reveal. Ampere proved that this grand total, the sum of the field all the way around our imaginary path, is directly tied to just one thing: the total amount of electric current that's actually flowing inside our loop.
And here it is, the law in its beautiful mathematical glory. On the left side, that sigma symbol, that's our grand total, from our walk around the path. And on the right side, it's simply equal to the current, I, times this fundamental constant of the universe called mu naught. You can just think of mu naught as a number that tells you how easily a magnetic field can set up shop in empty space.
So let's just let this sink in. This is the crucial aha moment. On the one hand, you have what we calculated, this complicated-sounding sum of the magnetic field measured at every single tiny point along our entire imaginary loop. And what does all that work equal? Well, it equals something incredibly simple. Just a constant multiplied by the electric current that's causing the whole thing. It's a deep statement about how elegantly the universe is put together.
So, okay, big deal, right? Why does this even matter? Well, because Ampere's law isn't just some abstract equation for a textbook. It's a true cornerstone of the physics that powers our entire modern world. It is the solid proof that electricity and magnetism are really just two sides of the same coin. And on a practical level, it's the tool engineers use to design everything from the tiny motors in your phone to the massive electromagnets used in science and medicine.
And that leaves us with one last, really fascinating question to chew on. We've just seen how an electric current can create a magnetic field. But can it work the other way around? Could a magnetic field all by itself actually create an electric current? Now that's a story for another time.